Here today my topic is about the principle of effective stresses and to solve a problem about effective stresses. The effective stresses, which is also called skeleton of soil. As we know that the load is transferred from material from particle to the particle of the soil, and these soil particles bear the load. So to study this behavior, Terzari at 1923 recognized that the force transformation and present the principle of effective stresses, which is based on experimental data, then apply for fully saturated soil. Now, Terzari related three basic stresses. Number one is total normal stress, which is equal to the sum of the pore water pressure and effective pressure. This is force per unit area transmitted in a normal direction across the plane, which while imagine the cell to be a solid, a single phase material. The second one is the pore water pressure. Is the pressure of water which is present and void between the solid particles. Now come toward our main topic, which is effective normal stress, which is the third number, which is called soil skeleton stresses, as mentioned earlier. This is the stress which is bear by soil particle, which is equal to the total stress minus pore water pressure. So this is the relationship of the total stress is equal to the effective stress minus pore water pressure. Now come toward a general physical model. The principle can be represented by following physical model. Consider a plane x-axis. The plane x-axis. Consider a plane x-axis in a fully saturated soil passing through a point of interparticle contact only, as shown in figure. The wavy plane x-axis is really indistinguishable from a true plane on the mass scale due to the relatively small size of individual particles. A normal force P applied over area A may be resisted partially by interparticle forces and partially by pressure and the pore water. The interparticle forces are very random on both magnitude and direction throughout the soil mass, but at every point of the content on the wavy plane may be split into components like normal and tangential components, which is represented by n prime and t respectively. Then effective normal stress is interpreted as a sum of all the component n prime within the area A divided by A, which is that equation. This is the effective normal stress is equal to summation of all the n prime's values vertical normal divided by area, this area. So the total normal stress is given by stress is equal to P by A. This is the P load acting on this area, the soil mass, and this is the area of this mass. This is the normal stress. Now, if the point contact is assumed between the particles, and the pore water pressure will act on the plane or the entire area. Then for equilibrium and the direction normal to the x-axis. So the pore water pressure will be, the total pressure will be, the P is equal to the sum of the normal which oppose that one, and plus the pore water pressure multiplied by this area. So we can write this like by dividing the both side by A area. Then we get P by A, and this summation of n prime divided by A plus U, which is pore water pressure. And this term is equal to the total stress, and this term is equal to the effect to the vertical stress. So before going to the calculation step, I wanna explain some things. Like the pore water pressure, which is act equally in all directions, will act on the entire surface of any particle, but is assumed not to change the volume of the particle. Also, the pore water pressure does not cause particle to be pressed together. The error involved in assuming point contact between particle is negligible in soils. A total contact area normally being between 1 and 3% of the cross-sectional area. And it should be understood that effective stress does not represent the true contact stress between two particles, which should be random but very much higher stress n prime by A, which is where A is the actual area between the particles. So now come to calculate effective stress in soil. First of all, we consider a soil mass having a horizontal surface and with the water table at surface level. First, we will find the vertical normal stresses for soil profile, which is normal to horizontal plane at depth Z, is equal to the saturated unit weight multiplied by depth Z. Then calculate pore water pressure at depth Z by multiplying the unit weight of water with depth Z. For calculating the effective stress, we use formula which is equal to the effective stress. Effective stress is equal to total normal stress minus pore water pressure, which will be found in about two steps. These two terms, the stress V and pore water pressure, is determined here. Then we put these two values here, then we get the effective stresses values. Also, we can find like this way by subtracting saturated gamma, saturated unit weight minus unit weight of water multiplied by Z. Then we get saturated prime, which is the bulk modulus. So now we go toward example of effective stress. Suppose we have a layer which is 4 meter saturated clay. This saturated clay technique is 4 meter and is overlain by 5 meter deep sand. The thickness of sand is 5 meter and the thickness of clay is 4 meter. And the water table is above the sand. So come toward this, from this surface to that surface is the sand, and from that point to that point is the clay. So the 3 meter below, from the top of the surface and the sand is the water table line, the position of the water table. The saturated unit weight of the clay and sand are 19 and 20 kilonewton per meter cube respectively. So above the water table, the unit weight of the sand is 17 kilonewton per meter cube. This is your gamma saturated for the sand, and this is gamma saturated for the clay, and this is gamma dry density. Unit weight of dry density of sand is 17 kilonewton per meter cube. So here the question is, the requirement is the value of total vertical stress and effective vertical stress against depth at the side of the height of 1 meter above the water table is saturated with capillary water. How? So we are concerned only here with these three things: effective stress, vertical stress, total vertical stresses against the depth. So here the depth, for example, we are studying for the depth this 3 meter above the water table. The above the water table the vertical stress is 3 multiplied by 17, which is equal to 51, and total vertical stress is that much, and the pore water pressure at that time is 0 because there is no water, there is free of water, dry. So we can use the formula to find the effective stresses, which is become by subtracting 51 minus 0 is equal to 51. So now come toward at that point, a 5 point, we want to find the stresses at that point. So 3 multiplied by 17 and plus 2, this the 2 distance, 2 multiplied by 20 to find the total stress is equal to 91. And while there at that place at 3 meter we have 0 pore water pressure, but at that point, at that sand point which is saturated, which is mentioned here, which is saturated. So as saturated, so we will multiply 2 with the unit weight of the water, which is 9.8 is equal to 19.6. So subtracting this value from the 91 is equal to 71, and 71 is the effective vertical stress. Like this way we go down, we want to find at that point the stresses. The 3 multiplied by 17 is same, and 2 multiplied by 20 is same, and the 4 multiplied by 19 for to find the total vertical stress. So again, from this water table, from this point water table is thought, so 2 plus 4, this total is 6. As 6 multiplied by 9.8, we get this one. So for subtracting this value from 167, we get 108.2. So that's all about the example. So we can solve this example by another way, like here. If we want to find only effective stresses at depth 5 and 9, at depth 5 and 9 here. So what will be happen? How we will find directly? We can do that like this way. 20 is the saturated unit weight of the for sand. 20 minus 9.8 is equal to 10.2, and 19 minus 9.8, which is saturated unit weight for clay. 19 minus 9.8, which is equal to 9.2 kN per meter cube. Then we can find effective stresses for this. The 3 for 5 meter depth. At 5 meter depth we want to find, if we want to find effective stresses, then S will be equal to 3 multiplied by 17, which is the dry unit weight, and 2 multiplied by 10.5, which is this one, which is that's bulk modulus. We can get 71.4, which is very equal to 71.4 is that one. Like this way we can find 3 multiplied by 17 and 2 multiplied by 10.2, this one, and 4 multiplied by 9.2, this one. Then we get 108.2 kN per meter square, which is equal to that one. So now we come to another example for effective stresses. For example, we have a soil surface shown in a figure. We have two soils, soil A and soil type B. Have a drying density is 17 km per meter cube. Have dry density is 18 km per meter cube. So the water table at that level. So they gave us the 18 dry density, this one. They say that with different dry density, the average degree of saturation of soil A is 30% and the average water table at 2 meter depth. Okay. Assume that the specific gravity is equal to the 2.7 for both sides. Calculate the following values for both sides, type A and type B, at 2 meter, at 5 meter. So now they say that total vertical stress at point P, that's point, total vertical or water pressure at U at point P, that's one, effective stress at point P, that one. So now we come toward first of all total stress at point P, as I mentioned earlier, and they gave us the dry unit weight. Then we will convert this dry unit weight into wet unit weight of the soil. That's one. That's is is equal to H70 multiplied by 1 plus water content. The water content is, as they mentioned, is 30% degree of saturation. So that one, then we get 18.06 kN per meter cube as weight unit to weight of soil. As like that one, total stress at point P will be what? We will use this one, and this the gamma values, and this the 2 meter SZ values. 2 multiplied by gamma, we get the total stress at point P. At that point, we have the soil is unsaturated. There are no water table, so at that point there are no water means no zero pore water pressure. So effective stress at point P is equal to subtraction of this value from 26.12 as by formula. We get the effective stress at point P is equal to 36.12. So that's all about the example. Another example. So I will show back you to show the diagram, how to draw this diagram. Let's see here. That's the diagram, the pathway for the effective stresses. This is the part for the total stresses. At that point, the effective stresses and the total stress is same, because at that point, up to that point, the pore water pressure is 0, and then the pore water pressure is added, and this is the difference of the pore water pressure as long you go. The linear changes, increase and changes. It's like you go down, then the curve is turned inside, because if we check these values, the densities, these values 17, 19 and 20, so this value is go down, and not like this way, because the pore water pressure will be subtracted. At that point is 9.8, which is too much, which is like you can see here is 10.7 to 10.2 as maximum, then 9.2. So the graph is going inside. That's all about the understanding the graph, how to plot this. Then we come toward the forces acting underneath dam embankment. First of all is the water pressure. Water pressure is the pressure of water that acts perpendicular to the upstream side of the dam, and the pressure increases as we go down, so it shown as triangle. So total pressure as an horizontal direction in act on the upstream face at a height of h by 3 from the bottom, which is the mass of the triangular forces. And the P1 is equal to W. The W means is the game of the water multiplied by h square, just the h height square, and divided by triangle 2, because this the showing the triangle. There's the triangle, so showing the triangle. This point is equal to WH multiplied by h divided by 2, which is equal to the area of the triangle. Then, if there are additional water at downstream, like here, which will act like stabilizing the dam from downstream, it increases the factor of safety, and act like to support the dam, while the value is very negligible. That's why the effect is neglected, because the water level is not that much to support that one. So the effect is very negligible, very small, so we neglect it. So now come toward the uplift pressure. An uplift pressure is any pressure exerted beneath a structure or retaining wall that has potential to raise the structure higher relative to its surrounding. Most common uplift pressure come from water pressure horizon around the structure. When the water is stored on the upstream side of a dam, then there exists a head of water equally to the height to which the water is stored. This water enters the pores and fissures and cracks of the foundations. Uplift reduces the effective weight of the structure, and consequently the restoring force is reduced. So come to order diagram for better understanding. We put two diagrams to better understanding. First of all, this one. Here's the height h1, how the effects of that much. You can see how much it affects the uplift effect, which is really dangerous for the dam. For the dams, which is loaded dams, earth-filled dams, have lateral effect, uplift effect. So to reduce uplift effect, we will do some mechanism also, and this is the how we calculate these pressures. This is the gamma W, which is the your unit weight of water, and this H is found like here, H2 plus x by L, H1 minus H2, H1 minus H2 multiplied by this x divided by the total length L. So then from there we can get this hx at that point, the hx, which is that one. When we get this hx, then we multiply hx with the gamma of water. We will find the stress, the pressure, uplift pressure. Like here we can for better understanding, it's the pH, which is the horizontal force acting of the water from that point, and this is the W load acting downward, and this is the uplift pressure, which is constant uplift acting due to this water's level, and this is the seismic uplift. Because of the seismic actions, they also produce uplift pressures. When the uplift pressure is more than the building, the dam resistance, the bearing capacity, the load, the weight, then this dam will be overlift. So come toward the example. Calculate the forces on the dam. A given dam F, gamma is equal to 2.5 T by m cube, and gamma W is the unit weight of water, is that one. HW is 1.5 meter. So that's the dam, 6 meter have a thickness, and that much this is the water level, 33 meter, and that's the above regions, and that's the 30 meters up to that level, and 24 meter that one. So first of all, we weight of water is the weight of the structures, a W1 in that one, and W2. By using this formula, we can find these weights and water pressures. And water pressure is equal to this is like a triangle. 1.1 divided by 2, which is equal to 0.5, multiplied by 1, which is the gamma W, multiplied by 33 square. 33 is that height, 33 square. So we get that one. Is like this. Uplift pressure is equal to 0.5, which is 1 by 2 multiplied by gamma W, which is equal to 1, and 33, which is equal to that height, and 24, which is the length. So we find the uplift pressure, left pressure, which is equal to 33, 96 T. So thank you.